Good afternoon, everyone. My name is Stephen Bates. I'm the Chief Technology Officer at Eideticom, and today I'm here at the 2020 SDC SNIA Computational Storage Bird of a Feather demo session to talk about our new transparent compression solution, which is a stacked file system that we call NoLoad file system, and how we leverage that and our NVMe-based computational storage processors provide application transparent compression. So I'm going to talk a little about NoLoad. I'm going to talk a little about our stacked file system, NoLoad file system, and then I'm going to run through a quick demonstration of us achieving transparent compression, finish off with some conclusions, and then open it up for some questions. So let's go. So I want to focus first on our computational storage processor itself, which we call NoLoad. So NoLoad is an NVMe-based computational storage processor. And what I mean by that is that we leverage the NVM Express protocol and standards to move computational processes from a host processor down to a computational storage processor solution. So if we dig into what the Eideticom NoLoad CSP looks like in the diagram on the right here, we can see we have an NVMe front end, which consists of a PCIe endpoint, an NVMe controller, and DMA engines. And we combine that with a group of computational offload engines. And those have been developed by Eideticom and integrated into the NoLoad NVMe framework. And we have computational storage services or functions like compression, erasure coding, dedupe, encryption, and more analytical functions like data analytics, such as regular expression, AI, and ML. We also have a controller memory buffer, which I won't dig into too much today. But the important thing is that this device and the computation functions provided by it are presented to the host over NVMe. And so we have a software stack that I'll talk about in a minute that lives on the host that ties applications to the storage services provided on the CSP. So let's take a look at that. If we look at this from a software point of view, on the host, we typically install either a user space library, which in our case we call libNoLoad, or we integrate a stacked file system, and this is the kind of new development that we're launching at SDC that we want to talk about today. So NoLoad file system is a stacked file system. What we mean by that is it's a shim that integrates between the virtual file system layer in Linux, just below the kind of user space, kernel space interface, and then sits above the actual customer chosen file system, such as ext4 or XFS. And what's really nice about that is we can provide application transparent services. So we can provide services, and today's example is compression, without the application needing to know the NoLoad is even in the system. But we also allow the customer to still use the file systems they prefer to use. So rather than having to move a customer from a given file system to a file system specifically created for compression, for example, the customer can stay on their own original file system, and we just integrate NoLoad file system on top. And in fact, one of our engineers, David Sloan, is giving a much more comprehensive overview of NoLoad file system at SDC. So I recommend you go check his talk out, and that will provide a lot more information on the specifics of NoLoad file system. And of course, the actual deployment of NoLoad is can be on many different types of hardware platform. So we can have add-in cards, we can have computational storage drives like the Samsung Smart SSD, and we can have storage form factor centric computational storage processors like we can have on the Bitware 250U2. So the kind of demonstrations or the kind of problems we can solve with NoLoad file system are allowing customers to run whatever applications they like in user space. So for example, that could be a database like MariaDB or RocksDB, such as shown on the left here. Or it could be something like a software-defined storage stack like Hadoop, or more specifically HDFS, which is the storage distributed file system component of Hadoop. And those applications are not needed to be modified. There's no user space changes required at all. And what we can then do is tie into the customer's file system. We leverage the NVMe driver that's in box, and then we can talk to either computational storage drives or computational storage processors or a mix thereof. So what we're going to do now is a demonstration. So if you'll just give me a moment, I will switch over to the demonstration window, and then we'll come back to the presentation and carry on from there. So let's walk through the demonstration. Oh. So first off, we're going to take a look at what's sitting on this server right now. So let's have a look at the block space. The most interesting part is at the bottom. You can see there's actually a RAID array here built up of a number of NVMe drives with an XFS file system on top. We also have an NVMe computational storage processor in there. And what we're going to do is leverage the compression capabilities of that and mount our NoLoad file system on top. So you can see David's issued a standard mount command where the type is NoLoad file system. So these are all sysadmin commands that are very, very intuitive to the sysadmins who are using them. We're going to create a couple of windows so we can walk through the demonstration. Eideticom, we do love tmux, so we do like to do things with tmux. Here we have IO stat on all the NVMe devices, and they'll be useful for looking at the drive. We also have our own tool, which is what we call NoLoad, and we're going to run the watch subcommand of NoLoad, which is going to let us look at some counters on the NoLoad itself. So what you're looking at in the window here on the top right are counters from the actual hardware. We want to see how hard the processor's working, so let's pull up HTOP. You can see this is a pretty big machine. We've got 32 cores. This is an AMD Rome-based system with a whole bunch of NVMe drives. And for the demo, we're going to use FIO as our user space application. And what we're actually going to do is write some very large files to disk, and these files are going to be 50% compressible. So the first thing we're going to do is write as fast as we can to these NVMe drives, but compress the data via NoLoad. And I think what's interesting here, if you can see my mouse, is if we focus up on the top right-hand side in the NoLoad watch, you can see we're hitting over 11 gigabytes per second of logical write data, which is being compressed by our U50 NoLoad in this case, and outputting about 6 gigabytes per second of compressed data, which is getting written to disk. And what's important is FIO, the user space application, has absolutely no idea that any kind of compression is happening. It's all hidden via NoLoad file system. Now what we're going to do now is do a read test where we're going to try and read back a whole bunch of this compressed data and put it back into the buffers in the user space process. And again, these are random but quite large I/O. So we're doing large I/O, but they are random over a very large file. And here you can see we can read even faster. We're reading off the disks at about 6.6 gigabytes per second, but the actual uncompressed data is double that, and we're hitting something just over 12 gigabytes per second, which is getting quite close to the limitations of this PCIe device, which is Gen 3 by 16 in this particular server. So all of this is running completely transparent to the application. You can see on the bottom right that the drives are getting hit with an awful lot of reads. So all the drives in this array are working pretty darn hard right now, but they'd be working an awful lot harder if we weren't doing compression, because we're reading them at 6.6 gigabytes per second, but we're getting over 12 gigabytes per second of user data. And again, I want to stress this is all being handled by the NoLoad file system. FIO has no idea what's going on here. It doesn't need to, and nor would any other user space application. And we're going to finish by doing a bit of a read-write test. So here what we're doing is we're going to do simultaneous reading and writing of the files that are on this stacked file system. And what you can see here is that we're actually able to read and write simultaneously at around 7 gigabytes per second in both directions. So that's the demonstration. As you can see, we do love tmux here at Eideticom. You can obviously replay this at your leisure and dig through some of these numbers in a little more detail. So I'm going to switch back to the presentation and finish that, and then we'll see if there's any questions. So let's summarize the results from that demonstration. On the right-hand side, we have the software stack that we used for the demonstration. We had FIO up in user space. That was just upstream FIO. And the scripts that we ran were kind of shown in the demo. And we're happy to provide those for people who would like to see them. Obviously, that kernel space consisted of a NoLoad file system integration and sitting on top of a standard file system. And then we had the NoLoad, in this case, on a Xilinx Alveo U50 card, and we had a whole bunch of NVMe drives. When we did write-only, we were able to hit 11.4 gigabytes per second of write traffic. And then that was compressed by about half. And then, so about 6 or so gigabytes per second were written to disk. Read only, we actually did a little better. We got 12.4. And then if we mix read and write, we were at the same time simultaneously able to achieve over 7 gigabytes per second of writes and 7 gigabytes per second of reads. And again, I want to stress, FIO had zero clue that we were actually doing any compression. The user space application did not have to change. So I hope you enjoyed this demonstration. We think transparent and stacked file systems are a very interesting way to do computational storage offload. Compression is the first service that we're shipping in NoLoad file system, but as you can imagine, we're thinking about many, many more. And obviously we have a roadmap for that. So if you're interested in learning more about where we think we can go with computational stacked file systems, reach out to me. Thank you for your time, and we'll open it up and see if there's any questions. So thank you very much.